Welcome. So in this part, we will apply what we learned before to an example. The objective are the same, like you basically be able to describe linearity, independence, homoscedasticity, normality of error assumption of your linear regression, and perform and interpret linear regression with real life data. Uh, so all these uh, lessons that figures that I'm showing you, this was done with Python, uh, for example. So here, this is data. Uh, this problem, I got it like here from Project Eddie. So you can go to Project, it's just modified from there. You can check it. This is a data source that I will be used. I got it from this site, the NASA, and basically the data have like temperature data, global temperature data. I will talk about it, and all the codes that you see here, like the analysis that was done with Python, so you can find, for example, like this problem. You can play with them. This is this example, like you can play with them. This is the multimodal example, for example, and these are the examples that we will be doing in this tutorial. So you can play and change them. If you want to learn how to do this with Excel, I will add another video. Basically, like this video is optional, you don't need to watch it, but if you like to know how to do regression analysis with Excel, there will be another video for that. But for now, whatever figure I will be showing you, you can check this Python code if you want to repeat this or like do this again with your own data. Yeah, and all the Python code will be provided. So perform and interpret linear regression with real life data. Okay. So let's just get started. So just to, if like, so this is our research question: is the Earth warming or not? So if the Earth is warming, what we would expect? Again, this problem is from here, uh, the EDI project. If the Earth is warming, then what we expect is that the temperature, you should have a positive trend with time. If the Earth is if the Earth is cooling, if the Earth is cooling, you should expect that the temperature will decrease with time. If the Earth is warming, you should expect that the temperature will increase with time. If there is no change, then you will not see like a change with time. Be something like this, yeah. So how to answer this question? That's easy. You just get the global, for example, Earth temperature, and just get like an annual average, yeah. So like you get the temperature for all parts of the world, like you can get this from some data products. We will use like one of the NASA data product for this, and then for each year you get the average Earth temperature, and then you plot it, and you see can you fit a trend line to it, and linear regression line to it, and basically your independent variable would be time and your dependent variable would be the Earth's temperature. Okay, so here the data product is the gas surface temperature analysis of NASA uh, uh, data, so you can check this data product. If you want to download it, you can download it from here. Yeah, and you will find instruction on how to download this data, and basically this is the one that is used here. And what we do is that like we don't need to print like plot the absolute temperature or like the actual temperature, but what you can do, you can just plot like a temperature anomaly. So temperature anomaly from the corresponding 1951 to 1980 means. So basically from 1950 to 1980, this 30-year period, you just get the mean value for the Earth's temperature, and then you subtract each year temperature from that mean value for this period. Yeah. And then so you'd expect like around this period, like you'll expect temperature would be like around zero, but then if the Earth's temperature increasing, then you see here that like this from this data, I don't know if this is like can fit like a linear model or not, because I see some linearity, non-linearity here, so you might fit like a model. Oops. You might fit a model. Maybe that looks like this, a little bit non-linear, like a quadratic model. But this part, like it seems to me like a linear part. So maybe if I ignore this part of the data, I can fit like a linear model here. Yeah, because you can different parts of the data you can fill different models for it. I mean, depending on what you want to do and your objective. But for this, let's just check our assumption. Let's just check the uh, linearity assumption. So to check, so here is like check linearity using non-parametric regression. So basically the non-parametric regression, this is a regression that does not assume any model. So it does not assume like polynomial with degree 1, degree 2, exponential or whatever. So one way like this is called Louise. Louise, this stands for locally weighted scatter plot smoothing. This is a non-parametric smoothing technique that basically estimates value at each point by fitting weighted regression line at localized subset of the data. So at localized subset of the data, you just fit a regression, revealing the underlying trend without assuming any linear relationship. So you don't assume any linear relationship and you see the trend. And like the trend, like here, up to like maybe starting from here, yeah, oops, starting from here, yes, you can see maybe this is part is like linear. Let me change this color. So starting from here, maybe this part is like linear. But maybe, or maybe starting from here, yeah. This part like seems linear, but or maybe here, yeah. But this part is kind of like non-linear, or like another like two linear, like or like you can fit like a linear line here and another linear line here, but this would be much steeper, which means that the temperature would be going much higher than this part here. So like I can, so like for this data, I can just fit maybe one trend line here and another trend line here, and that would be more steeper, something like this. But anyway, so we know that non-parametric regression might not be, sorry, like linearity is not really satisfied here. But anyway, we can check the other one, homoscedasticity, like whether this data is uh, like the constant variance, and you don't see like this funny thing like that. Oops, you don't see this funny thing where like the variance is increasing, for example, as the value increase, yeah, as the fitted value increase, which is the temperature anomaly. So the temperature anomaly from negative 0.2 degrees centigrade to 0.8 degrees centigrade. So you don't see any variance. So basically, like the residual, in that case, they appear to be randomly scattered around the zero without like a clear pattern. Maybe there is like kind of a funnel shape here. Remember we saw this funnel shape. Maybe there like especially like here there's something. Maybe there's something here funnel shape. Uh, but overall, like maybe is a homoscedasticity assumption. Maybe it could be a little bit violated, but we can just see. Okay. Now let's look at our normality check. And normality check, basically you get like your residual and you make a histogram for your residual. And the histogram for the residual, if I will fit like a bill, like it does not, I mean, it's not bad. Like you can fit maybe kind of like a normal distribution to it, something that looks like this. So the residual appear randomly scattered around the zero, but they are randomly scattered around the zero. They might not be like a perfect normal distribution, but they are randomly scattered around the zero without uh, so like the normal distribution might be looks good, but remember, like how do we check for normality? We check mainly for normality through the QQ plot. So let's do the QQ plot and see the QQ plot looks good. So they are on this. So this is the sample quantiles and this is the theoretical quantile, and this if they lie together, this means that my residual are more or less like normally distributed. So that fit is not bad. Okay, so the normality check seems okay. So here like the uh, linearity check is maybe not so good. The homoscedasticity check seems okay. The normality check seems okay. The last one is autocorrelation, and we got for this one we got Durbin-Watson statistic of one residual exhibiting a mild positive autocorrelation. So what does this mean? That this means that you got the, remember, if it's two, then there's no correlation. If it is like closer to two, so this means that the residual they exhibit a mild positive autocorrelation, suggesting that independence assumption may not be fully met. So your independence assumption is not fully met, uh, and so that might suggest that there might be autocorrelation in the data. But overall, like the independency assumption seems to be satisfied because you don't get like strong autocorrelation. So roughly, yes, we can use linear regression here. So given our residual analysis and other consideration, can we use this model to project Earth's temperatures? That's my question. But before this, before I even ask this question, can we use this model to answer our research question, which is the Earth's temperature warning? Yes, we can, because it's clear, like, even though some of our assumptions are not kind of satisfied perfectly, but still we can see we can like use this to answer our question, because like we see here a clear trend, even though there might be some non-linearity here, that might not be the perfect line to fit to this, but there is a clear trend of that. So the main question is, the Earth's temperature rising? Yes, it is rising, because we see a clear trend. Here is the slope and this is intercept. Yeah. Now, the second part, can we use this model to project Earth's temperature? So now the temperature now is in 2020, we have a temperature anomaly. We are almost like at 1 degree. Yeah. So in mid-century, like 250, or like the end of century, can we use this model to predict temperature at the mid-century and end of century? What do you think? So I want you to pause the video and answer. Of course you can, but like, is this meaningful to do it? So here, for example, like if I want to just project in the future, so if I projected in the future in mid-century, I will have like a temperature rise of 1.27. At the end of century, I have a temperature rise of 2 degree. But is this reliable? Like, is this result reliable? Can we use this result? And the answer, of course, is no. Why? Because first of all, we are fitting like a linear model to something that does not seem linear. So maybe, so this model is somehow like, maybe you should maybe fit two models here, like one model here and another model here. And if you did this, then the slope of this guy would be much steeper than 0.02. So this number might not be 1.27, it could be maybe 1.5, and this could be like 2.5, for example, because you have a steeper slope. Second of all, is like the validity of the linear model here might not be valid. So here, even though like we have a r square, which is very good, which means that like time really explains my dependent variables, the change of temperature, but the linear model might not, like if you want to do this type of projection, linear model might not uh, be the best case if you want to project like current condition to the future, like mid-century or and or like current trend, yeah, like the trend, and because that could be like a non-linear relationship, that there's some non-linearity that we need to account for, and we need also to and this is just simple projection by just like assuming that uh, the underlying driving force will not change, which is not the case because the underlying driving force is changing, as that could also create some nonlinearity. Uh, so here, basically, like, can we answer the first question? Is the Earth's temperature warming? The answer is yes. Can we answer this question? Can we use this model to project the Earth's temperature? The answer is no for this question. Okay, so you should be careful about like how to use your model. Okay. Now this is just appendix ordinary least square result from stand mods. This is the Python code that I used for solving this, and you can check all the codes. All the codes are provided, so you can check, for example, like yeah. So this would be like the result of this stand mode results. Here, these are the uh, data, the true models that I use to generate the data for different problems that I showed you. So this is the true model where the data were generated from. Usually in real life, we don't know this. Like for example, for this global temperature exercise, we don't have an equation like this because the data we didn't generate, this is not synthetic data. This is actual data that we collected. Yeah. Based on remote sensing. This is a model for the multivariable regression. If you want to learn more about the assumption uh, of least square method, you can check this paper. It will show you more about these assumptions. And one thing which we didn't discuss in any of these videos is the implication for violating these assumptions, and how can also one thing we didn't discuss is how can you account for these assumptions if you want to, like if your data is like not does not have a constant variant, how can you account for this? If your data has autocorrelation, how could you account for this? If your data does not follow a normal distribution, like your residual does not follow normal distribution, how could you account for this? If your data is non-linear, that's easy, just use a non-linear model. Yeah. So you don't need to do much. Okay, so that's all I think for this lesson and for this module. And yeah, see you in other videos. Okay.